Good morning. I am Rebecca Wright, Chair of Computer Science at Barnard College, and we're here today for our computer science seminar. We're happy to have Heather Newman with us. She is a PhD candidate in the Interdisciplinary Algorithms, Combinatorics, and Optimization program at Carnegie Mellon University, advised by Benjamin Mosley. She works at the intersection of theoretical computer science and operations research, with a focus on the design and analysis of algorithms that are provably fair, fast, and robust to uncertainty, particularly for problems in clustering and resource allocation. And her research has been published in top theory, ML, and operations research venues, including ICALP, ICML, and Math Programming B. Her undergraduate degree is in mathematics from Princeton University, and she also has a master's degree from mathematical sciences from Oxford. Heather, the floor is yours.
Thank you for the introduction. So yes, my talk is titled The Best of Both Worlds, Fast Clustering Algorithms for Simultaneously Optimizing Fairness and Average Welfare. As was said in the introduction, I mainly work in theory, but I've designed this talk to be accessible to undergraduates who may not be in theory. But if anything's sort of unclear, I am happy to take questions. The talk is timed to be around 40 minutes. So I think we should have time. So feel free to interrupt me. Okay, so, I don't know if this clicker is working. I'll just, okay. So I'll talk about a specific series of works, but I want to start with an overview of my research more generally. So I am interested in the design and analysis of algorithms that are fast, fair, and robust to uncertainty. I will focus on the fairness thread today, but I will also talk about these two other threads. But I just want to give a sense of what I mean by these three threads. So the first one, fast algorithms. So data sets are very large in today's world, and we need algorithms that scale to their size. So for instance, today I'll talk about social networks, and social networks can have hundreds of thousands of nodes. We need algorithms that scale to that size. We can't sort of just look at these networks and extract their properties. So that's one example. And I want to talk a little bit about the interplay between theory and practice here. So in theory, we have this idea of what a fast algorithm is, and we have this famous P not equal to NP conjecture that tells us that there are certain things that we don't think we can do fast. But this is a theoretical definition. Often practice isn't reflective of theory. So something that is fast according to this theoretical definition might not be fast in practice. And then there's an interplay in the other direction, which is often theory is not reflective of practice. So in theory, traditionally, we have looked at worst case guarantees, which is to say, what's the worst that our algorithm could perform on any instance. In practice, maybe we are not seeing those instances, and maybe we want practice to inform our theory. So maybe we want to parameterize our algorithms by some characteristics of the instances we see. So I like to think of this interplay in those two directions. Okay, fair algorithms. So today I'll talk about building fairness into our objective functions. So for instance, some applications of this might be in resource allocation problems. So just as a toy example, maybe you're allocating gifts to children and you want to maximize the happiness of the least happy child. And okay, it sounds a little silly, but you can think of this more generally. So that would be a fairness objective, or maybe you're allocating jobs to machines and you want to minimize the wait time of the job that is waiting the longest. I would consider that a fairness objective. There's another way that we can consider fairness, which is we seek outputs that capture fairness. So as an example, in healthcare, there's this problem of patient segmentation where you want to divide patients into groups with similar comorbidities so that you can personalize care. And you might want certain fairness constraints on these groups. For instance, you might want proportional representation of protected features like race or gender or age. So you want to build in that aspect of fairness into the outputs you're seeking. And then finally, I'm interested in robustness to uncertainty. And this can mean a lot of things in a lot of different communities. But the two types of uncertainty sources I like to think about are when your input data is uncertain, so you don't have access to all of the data at once and it's arriving on the fly, but you have to make irrevocable decisions without knowing the future. And you would like those decisions to be hopefully approximately as good as if you did know the future. And another source of uncertainty can be that your input data itself is unreliable. There's some noise and you want to be robust to that noise. Okay, and I mainly like to address these threads using tools from optimization, which I'll talk about today. So, but hopefully, maybe what I can convince you of is that heuristic development of algorithms for these problems is not sufficient, and we need a deeper structural understanding that we can gain through theoretical treatment. So that would be my bias as a theoretician. Okay, so my specific area is approximation algorithms. So I'm going to define this very precisely. So I'm interested in optimization problems, so problems where we want to minimize or maximize some score that we assign to the quality of the algorithm's decisions. And this score is popularly known as the objective function. And this is something we choose. So there's a degree of sort of arbitrariness here, and that will be part of the talk. So I just want to emphasize that. And I'll be in the setting where we're minimizing this objective function. So just as a very toy example, there's this problem of vertex cover and graph theory. So you have a graph and you want to seek a set of vertices that covers all edges. So this is, okay, best seen through example. So maybe we're trying to build this vertex cover. We choose this vertex A. It covers the edge incident to it. Then maybe we choose C. It covers these 3 edges. Then we choose E. It covers these 2 edges. Finally, we choose G. Covers the last edge. So we have a set of 4 vertices. They cover all edges in the graph. So a reasonable objective function would be the total number of vertices, and we would seek to minimize this. So this is not the best you can do here. So for instance, these 3 vertices cover all the edges. And you can convince yourself that you can't do better than 3 here. So that would be the optimal objective. Okay, but there's this inherent trade-off between solving to optimality and solving fast. And our definition of fast in theory is your algorithm should run its time polynomial in the size of the input. And we have these so-called NP-hard problems. Roughly speaking, we think we cannot do both for certain problems like vertex cover, both solve to optimality and solve fast. So then in the field of approximation algorithms, we want to relax one of these 2 goals. So we decide to relax the optimality goal and we'll settle for near optimality. And what do we mean by that? Well, let's take a look back at this vertex cover problem. So I'm calling this graph instance I of the problem, and algebra is just the cost of the algorithm we ran on this graph, and that's 4. There are 4 vertices. But the optimal for this instance is actually 3. And so then you want to ask how far off is your algorithm's cost from the optimal cost? And in this case, it's 4/3. And you would want to know what this ratio is in the worst case over all instances, so over all graphs that you could see. And that's what motivates the definition of approximation ratio. So we just take the ratio of the algorithm's cost to the optimal cost for a given instance, and we look at what's the worst instance, so the worst gap we have in a multiplicative sense between the algorithm and the optimal, and that's the approximation ratio. So this is worst case analysis. And our goal is to find an algorithm with small approximation ratio. And we would call that, in this context, a near optimal algorithm. When we say small, we mean around a constant, maybe like a constant, like 5, or even in theory, people would be interested in like a constant of 1,000. Are there any questions about the definition of approximation ratio? Okay, great. So I'm going to talk about a clustering problem. So clustering refers to a class of many algorithms where the goal is to group objects together based on similarity. And today I'm going to be talking about a model called correlation clustering, which is a very expressive model that captures a lot of applications. For instance, finding communities in social networks, clustering gene expression patterns, image segmentation, where you want to sort of separate foreground from background, but I'll focus on the community detection application just for concreteness. Okay, so what is the model? So I'm using the social network example. So we have some group of people, and let's just say a pair of people are either friends or strangers. And there are other models of correlation clustering where you could take this a step further and sort of weight how closely related people are. But that will be our model, and it's the most popular one, I would say. So you convert this social network into a graph where there's a node for every person, and between any two people, there's either a positive edge, which indicates that they're friends, or a negative edge, which indicates that they're strangers. So you convert this into a complete graph. And more generally, if you have a positive edge between two objects, let's say, it represents similarity. A negative edge represents dissimilarity. So you could use that rationale for these other applications. And the goal is you want to partition the vertex set into clusters. So partition the vertices into groups where you want to group similar nodes and separate dissimilar nodes. That is the goal. And maybe unlike other clustering problems that you might be familiar with, like k-median or k-means, we don't pre-specify the number of clusters. So that's not part of the input. And well, why is this problem sort of hard? Well, people's preferences are inconsistent. So for instance, here, person 2 wants to be grouped with person 1 wants to be grouped with person 3, but 2 and 3 don't want to be grouped together. So it's not clear how you should design a clustering to address these sort of inconsistent preferences. So one example would be maybe group 1, 2, and 3 together, then 4 on its own, and 5 on its own. And I'll call this clustering C. So now we need to say, we need to design an objective function. What do we consider a good clustering? So all objective functions I'm familiar with for correlation clustering use this notion called disagreement. So we'll call an edge UV a disagreement with respect to the clustering if it's either a positive edge, but its endpoints are in different clusters, or a negative edge, but its endpoints are in the same cluster. So in other words, the clustering is violating how the endpoints of this edge want to be grouped. So for instance, this edge between 2 and 3 is a disagreement because it's a negative edge, but its endpoints are in the same cluster. Whereas these two other edges, 1, 4, and 1, 5 are positive edges, but their edges are in different clusters. So the clustering is violating the preferences of the edges. And that's when we have disagreement. So a reasonable objective might be find a clustering that minimizes the total number of disagreements. And I'll call this in my talk like an average welfare objective. And hopefully there aren't any economists here who are going to take issue with that, but that's what I'll call like a welfare objective. But an equally reasonable objective would be maybe you want to minimize the maximum number of disagreements incident to any vertex. So here, the maximum number of disagreements incident to any vertex would be 2, because vertex 1 has 2 disagreements incident to it. So you want the least or the worst off person to be sort of as happy as they could be. So this is a fairness objective where you're looking at individuals. Okay, and this is sort of a spectrum here. So let's take this a step further. So I'm going to let YC of B be the number of disagreements with respect to C incident to B. So just if B is 1, for instance, YC of B is 2. And now you could create infinitely many objectives between these two in the following way. So we can rewrite the first objective. Minimizing the total number of disagreements is the same as summing the disagreements incident to each node over all nodes, and then finding the clustering C that minimizes that. Here you're counting each edge twice, that's fine. It's the same objective as minimizing the total number of disagreements. Or you could have this min-max objective where you look at the disagreements incident to every vertex and maximize that over all vertices and find the minimum clustering that does that. Okay, or you could interpolate between these two, and you could pick a parameter p, so think of p as a real number that's greater than or equal to 1, and you could sum over yc of v raised to the p. So as p is getting larger, it's penalizing vertices that have a large number of disagreements incident to them. So for concreteness, if p equals 2, think of this as the variance of the disagreements. That's probably the most popular objective that interpolates between these two ends. And I will call this middle objective the LP norm objective. And the goal is to minimize that quantity. So the top one's p equals 1, the bottom one is p equals infinity. And for any p greater than or equal to 1, you get an objective in between. So the details aren't so important, but just know if p is small, this is capturing a more global objective, which I'll call average welfare. If p is large, it's capturing something more local and prioritizing fairness. So there are infinitely many of these pretty natural objectives to choose from. And you might ask which one is the right one that's going to tell us how good our clustering is. But it would be nice if we didn't actually have to choose. So that idea is the thrust of this talk. So our research question was, can we find a single clustering that is near optimal for all objectives simultaneously? In other words, you don't have to identify what objective you're optimizing for. Maybe you can optimize for all of them at the same time. And if so, can you do it fast? I think it's an interesting question just as an existence question, but it would be nice if you could also get an efficient algorithm to do it. And when I say near optimal, I mean in the sense of approximation ratio that we talked about. So just to rephrase this first question, another way of thinking about this is, do you actually need to sacrifice average welfare for individual fairness? And our answer in our work is surprisingly no. One sense in which I think this is surprising is if you look at other clustering models, like k-median would be an average welfare objective, k-center would be a fairness objective. You actually do need to sacrifice one for the other, provably, as in there are lower bounds that say you need that. So it's interesting to find a clustering algorithm where you don't need that. So surprisingly no means you can find a single clustering that is near optimal for all the objectives simultaneously. And that is why I called this talk the best of both worlds, average welfare and fairness at the same time. Technically, I would say it's all worlds, because there are infinitely many objectives in between, but this was a more accepted idiom. Okay, so that's the question. But maybe I want to convince you that you can't sort of take any algorithm for one of these objectives and expect it to do well on the other. So we're going to need to work a bit for this. So let's look at a toy example. So you have this graph with n over 2 vertices on each side, and most of the edges are positive, so everything I haven't drawn is a positive edge, and then there's this negative matching in between. Okay. So there's this famous algorithm in correlation clustering called the pivot algorithm, and it works as follows. You randomly choose a pivot, which is just an unclustered vertex so far, and you grab the pivot's unclustered positive neighbors, and you make that a cluster. So remove that and recurse. And intuitively, this makes sense because you want people to be grouped with their friends. This is not so much directly saying anything about negative edges wanting to be separated, but at least at a high level, this is maybe a good algorithm. So maybe my unclustered vertex, my pivot that I start with is this top left one. I grab all of its positive neighbors, remove that cluster, and then I'm left with one vertex. I put it in its own cluster. And all of these edges in the middle, except for the top one, are now disagreements because their endpoints are in the same cluster. And then you also have all of these positive disagreements from this top right vertex that has been separated from all its friends. So you have around n disagreements incident to that vertex. So I'm letting alg1 be the cost of this algorithm that I just ran for the p equals 1 objective, which was the average welfare objective. So So this is around n, and I don't care so much about constants because I'm in the approximation world. And you could convince yourself offline or believe me that the optimal for the average welfare objective would also be around n. So this algorithm is good from an approximation ratio perspective for the average welfare objective. But what about for the fairness objective? So this vertex at the top right isn't so happy. So let's look at an alternative where this vertex is happier. So maybe you just put all of the vertices. Yes, sorry.
So you cannot just put everybody on the left, everybody on the right in clusters and have a movie.
Oh, okay. So it's a complete graph setting. So yes, everything that I haven't drawn is positive. But thank you for the question. Okay, so yeah, maybe you put all the vertices together. Now every vertex has exactly one disagreement incident to it. So this is better from a fairness perspective than the previous clustering. So this clustering on the right actually proves that for the fairness objective, so that's p equals infinity, the optimal is 1. But what this algorithm is doing on the left is getting a fairness objective of around n because of that vertex that's unhappy on the top right. So this is a very bad gap in terms of approximation ratio because we want to think of n as being arbitrarily large. Whereas this clustering on the right is actually good for both objectives. So the algorithm and the optimal are doing around n for the welfare objective, and they're both doing 1 for the fairness objective. So this is a clustering that's simultaneously good for both objectives. One thing I just want to point out is that in general, the optimal welfare objective and the optimal fairness objective will have different values. That's fine. That will always be true. What we're asking for is if the same underlying clustering. Okay, so this example proved that pivot is not going to give us what we want for our goal of not trading off welfare for fairness. You can prove that it is good for the welfare objective, so it gets a constant approximation ratio. But we just showed it's not good for the individual fairness objective. So pivot is not going to be what we want. Okay. So now I'm going to take a little detour into what inspired our approach. So I'll talk a little bit about past techniques and what we did differently. So we can model this correlation clustering problem with an integer linear program. The details are not important here. But the idea is we have some variable xuv. It's supposed to be set to 0 if you and v are in the same cluster, and 1 if you and v are in different clusters. And then we have some constraints. So the bottom constraint says just that. Then we have these triangle inequality constraints, and it's not so important how you derive them, but just know that these constraints encode that you want to partition the vertices into clusters. So they just encode feasible solutions. And then the line third from the bottom is just this setting of yu says calculates the disagreements incident to u. So the first sum is calculating the positive disagreements incident to u, and the second sum is calculating the negative disagreements. But again, it's not important, really. And the objective, the average welfare objective would be minimize the sum of the disagreements. So this is an integer linear program perfectly capturing our problem. And you can adjust the object. Oh, okay, so one thing I should say is this is not generally practical to solve in the sense of hardness. So, and it's because of these constraints, these integer constraints. And you could change the objective here. So this would be the fairness objective. And then you could use any of those objectives in between. I'm going to call it a linear program, regardless of what objective you use. But technically, if I use one of those LP norm objectives, now it's a convex program. But the constraints are linear, so I'm just going to shorthand that. Okay, so this models our problem, but it's not a practical way of solving it. So you can instead tweak this a little. So I'll call this the relaxed linear program. And the only thing I've changed is I've now let xuv range from 0 to 1 and not necessarily be integral. So now this is not really capturing our problem anymore because xuv is supposed to indicate to me whether u and v should be in the same cluster or not. And now it's sort of fractionally indicating that. But the advantage of this is that it can be solved to optimality efficiently. So maybe we can still use this, even though it's not capturing our problem. And I'll call an optimal solution to this x star. And again, I could encode any one of these objectives from welfare to fairness, but I have to specify that in order to, for instance, give this to a solver to solve it efficiently. But the hope is I can still use these fractional values of x, u, v. So remember, x star is the optimal solution. And if x star u, v is near 0, I want to think of that as this program suggesting to me to put u and v in the same cluster. And if x, u, v is closer to 1, I want to think of that as suggesting to me that I should put u and v in different clusters. So that's sort of the interpretation of the optimal solution you get out of this. Another way I want to look at this is, because I have these triangle inequality constraints, I can think of these x, u, v star as distances between u and v. And because I have these sort of probability constraints, I can think of them as, again, probabilities of separating u and v, which is in line with this interpretation on the bottom. Okay, so the question is, how can we use this, I'm going to call it advice, x star, that this linear program gives us to design an algorithm? So let's look at what past techniques did. So the idea is you have these fractional values telling you some sort of probability of how you should cluster the vertices, and you need to round them up to 0 or down to 1, depending on whether you want to separate or group vertices. So there's this ball cutting algorithm to do this, and I'm not going to go very low level, but the idea is you want to find a point with a dense ball around it. I'm not going to really go into what that means, but a point with a lot of points nearby according to this distance metric that x star gives us. And those points want to be grouped with that point in the middle, so we'll do that. We'll remove that cluster and then recurse. So this is what I'll call the ball cutting rounding algorithm. So the outline of that algorithm is you choose an objective function. So you choose p. So you choose, what trade-off you want essentially between fairness and welfare. You solve this problem to optimality. You get this optimal fractional solution x star for the specific LP norm objective that you chose. Then you input this into the ball cutting rounding algorithm, and then you get a clustering. And it turns out past work showed that the clustering that you get is an approximation ratio of 5. So that's good. That's constant. We like that. But it's for the p you chose. So in order to even have solved this linear program, you had to choose p. So already this is not so good for our objectives of ignoring p, essentially. So the clustering solution depends on the chosen objective function. That's not what we want. So what if we could instead bypass this step of choosing p? So this is now where I'm going to describe our idea. So we don't want to choose p, and thus we don't want to solve this linear program exactly. But the idea is we want to construct a guess of a feasible solution to this linear program. And the idea is when we're constructing this guess, we shouldn't have an objective in mind. So we shouldn't have a value of p in mind. So we want this guess to be good for all of these p. And I'm calling this the correlation metric, and I'll call it d. But what do I want it to satisfy? I still want to be able to interpret it as a distance. So I want it to satisfy the triangle inequality constraints. And I want to be able to interpret it as a probability. So now I want to interpret, or I want to construct this d so that if d u v is near 0, it should be somehow capturing that u and v want to be in the same cluster. And if d u v is near 1, u and v want to be in different clusters. So that's my goal now, to construct a guess that is somehow good for all of these objectives simultaneously. And what will I do? Well, instead of now solving this program to optimality, I'll replace x star with d, the correlation metric. I'll use the same ball cutting algorithm from previous research, and then I'll end up with a clustering that hopefully has a constant approximation ratio for all p. Okay, so how do we construct this? D has a very simple definition. So the definition is set DUV to be 1 minus the mutual friends of UV over the total number of friends of U or V. So that's how we set the correlation metric. And you know, you don't have total flexibility here, right? Like it has to satisfy the triangle inequality. It's easier to satisfy the probability constraints, but it should, you know, fit in with those constraints. Good. So let me just give some intuition for why this is a good metric for what we're trying to measure. Okay. So in the graph on the left, I've partitioned the positive neighbors of U or V into 3 sets. So I can point here. So this top set is the set of mutual friends. And the second set is the friends of U, but not of V. The third set is the friends of V, but not of U. Okay, so these are the 3 sets that are being considered in the definition of the correlation metric. And I claim that if this top set is large relative to these 2 other sets, then you should want to put U and V together. Well, let's consider what happens if you don't. So suppose you separate U and V, like we did here. Then, well, look at these top vertices, the mutual friends. Maybe you group them with U, but now they're separated from V, and V is unhappy. So you would incur a large number of disagreements that way. So if this set of mutual friends is large relative to the total set of friends between U and V, the idea is you want to put U and V together. On the other hand, if this set of mutual friends is small relative to the total set of friends of U or V, then I claim you want to separate U and V. Well, let's suppose you didn't. So let's suppose you put U and V together, right? Then look at this middle set. These friends of U want to be placed with U. But if that happens, they also have to be placed with V. So then you're getting a large number of disagreements incident to V because the strangers of V don't want to be grouped with V. So that's the intuition behind the definition of this metric. If the number of mutual friends is large, DUV is small, U and V want to be clustered together, and similarly for the other scenario. So that's our guess. And I'm not going to go into the proof of why this is good, but the heart of the argument is, you know, showing that this correlation metric is good for all of those norms. So it's a good guess, or a good approximate optimal solution to the linear program we saw on the previous slide. That's the heart of the argument. Showing triangle inequality is technical, but pretty straightforward. Okay, so in reality, we actually have to adjust this a little bit. So we don't use D as is. We tweak it a little bit in not so important ways for this talk, although important for the paper itself. And then all we do is input in the ball cutting rounding algorithm, get a near optimal solution for all objectives. And that is the result. Okay. I just want to mention a few properties. This correlation metric is based on explicit observable properties of the graph. So it's just based on whether people are friends or not. Whereas if you think back to the linear program, you know, we solve it to optimality by performing some general purpose linear programming algorithm. And while the output is very useful for designing an algorithm, it's not so interpretable. We don't know how the optimal solution to the linear program relates to combinatorial properties of the graph, like mutual friendship, for instance. So it's sort of a black box, whereas this is very explicit. This metric doesn't depend on P, so that would be somewhat important for our goal. And yes, it turns out this does give you a near optimal solution for all P. So our question was, do we actually need to sacrifice average welfare for individual fairness? The answer is surprisingly no. I mentioned one sense in which this is surprising, which is in other clustering models, you do need to sacrifice these objectives. But on a technical level, it's kind of surprising because usually you cannot solve for global objectives using only local information. And I would consider this correlation metric local information in that to define DUV, you only need to know about the friends of U and V. And finally, I think this suggests that correlation clustering has some unique combinatorial structure that we can exploit. And another sort of nice side effect of this new approach was the structural insights we gained had some other advantages. So one advantage was big gains in runtime. So I am a theoretician, but I did run this. I think it's good to do that. And so we ran this, for instance, on these 5 social networks. They are very small for social networks. So the largest one is 224 nodes. These runtimes are in seconds. So the previous state of the art took a little over 30 minutes, and our algorithm ran in 1/10 of a second. So that suggested this was more scalable. So then we ran this on larger networks. So this last network on the bottom is a collaboration network of physicists. It has around 12,000 nodes, 237,000 edges. And we ran in just over 4 minutes. So that was a nice side effect of this algorithm. And then more generally, I think the technique potentially gave us powerful and adaptable tools for other models. So one model we're working with that is the work is forthcoming is when your input data arrives on the fly. So maybe you don't have access to the social network in full up front, but you still have to make clustering decisions without knowing what the future network looks like, and you'd like to be robust to that uncertainty. Another maybe useful application would be what I talked about earlier, fair outputs. So maybe you want your clusters to have proportional representation of certain features like age or race or gender. We think because our algorithm is combinatorial, this could give us a tool for this setting. And more generally, maybe this technique of sort of guessing a good solution to a linear program could help us get best of both world solutions for other clustering or combinatorial problems. Okay, thank you.
Great. Thank you, Heather. So we can take questions in the room, in which case, unless it's from me right here, right now, I'll ask you to repeat the question so they can hear you
sure.
on Zoom. We can take questions on Zoom. I'll watch the chat and I will ask those questions, or also you can unmute yourself if you're on chat, or raise your hand, and then we'll call on you to unmute. So questions for Heather? I'll start with one. Oh, since I'm standing here, then I can sit and you can ask yours. So my question was, so of course there's some social networks where this friendship relationship isn't symmetric, like following, say. Would your algorithm or something, a similar tweak work to solve that as well with near optimality?
Oh, as in you sort of have a direction on the...
Right, so in the clustering, like even the two of us might disagree about whether we want that to be in the same cluster or not.
That's really interesting. I have not seen models of correlation clustering that capture like an asymmetry, even when you have a specific objective in mind, like welfare for fairness. It may exist, I just haven't seen it, but I think that's really interesting. The main generalization of this model that I'm familiar with is the weighted model. So instead of these binary classifiers, yeah, there's some strength assigned to the similarity or dissimilarity, but that does not capture asymmetry. So I'm not aware of it, but it's very interesting.
Well, thanks. That's quite interesting.
Thank you.
I was curious about in typical case where you try to do community detection. There you want to have some of those metrics, but the results matter. For instance, if the algorithm answer one cluster with everybody, even if that maximizes your objective, it's totally useless. So I was wondering, especially in the context where you have social networks that may have the typical property being sparse and some of the other property, what will happen if you try your algorithm? Will you have lots of clusters? Will you have just a small amount? What's going to matter? I'm very curious to know that.
Yeah, I think that's a good question. So as the model is stated, and as the objective functions are stated, measuring disagreements and coming up with a function based on that, like you don't necessarily, like in K-median, for instance, it's always better to be able to allocate more centers. And that's not actually true in this model. For instance, if you had all positive edges, then you don't want to use more centers, so or more clusters. But there is a version of this problem where you also fix the number of clusters, so you input a specific K. The guarantees, I think, in terms of approximation guarantee and runtime aren't so good, so I think the existing algorithms depend on K, which maybe is fine because in practice, like K might be a small constant. And yes, it is true that social networks tend to be sparse in practice. So one thing we looked at was, can we parameterize our analysis of this algorithm by the sparsity? So if for an appropriate definition of sparseness, we can show you get a much faster runtime if the network is sparse. That doesn't so much answer the question of, yeah, do you have like many small clusters? Maybe that's not so good. I think when I ran these on these sparse social networks, you do get some of these very small clusters, and maybe you want to do some post-processing on that. But yeah, you could also use a model where you actually do build in a restriction on the number of clusters.
But you shouldn't have ridiculously small one, because then it becomes very unfair to that node who is alone. So
that's true.
Terrible. I mean, that's why I think you might have something.
Yeah, I think that's a good point. That because you're building in the fairness objective. Yes, I agree. Yeah, I don't remember. I think so this is based on a series of 2 papers. So in the first paper, we weren't considering all objectives simultaneously. We were considering just the min-max objective, so the fairness objective. And for that objective, you can just use the correlation metric. You don't actually have to tweak it. But forget what I was going to say about your question. Yeah, in any case, right. It's good to, I think that is a benefit of the building the fairness objective.
All right, great. Heather, thank you again.
Thank you.
Bye, folks on Zoom. Thanks for participating.